So if you see in the previous sessions, we have been dealing with k-nearest neighbors, and then I showed you one of the implementations which we called as like simple implementation or standard implementation. So now I told you that there are different versions of KNN. So as you saw in the time complexity, it has order and d complexity, and in terms of space complexity, it again has order and d complexity. So then we have different versions of KNN which try to sort of reduce the time complexity, and there are other versions of KNN which try to like overcome different problems that KNN standard KNN has. Okay, let's first discuss the problems, then I'll ask you what are the solutions that you propose. So and then we'll try to formalize the solutions, and then we can go on with that, and we'll try to build your intuition behind that. So as you know, let's discuss for the standard KNN again. Standard KNN. So in standard KNN, what we had is, I won't write the algorithm, I'll just show you what it has. For example, if we have two clusters like this, let's suppose this was one cluster and this was another cluster. And if this was a query point, what we did is, if it's, let's suppose 3NN, three nearest neighbors. So we'll compute the distance of this, and these three neighbors. So then let's suppose we have D1, D2, D3. Actually, we'll compute all the Dn. So we'll compute all the Dn. Okay, then what we'll do is, if the values are like this 1, 5, 8, 6, 3, something like that, then we'll sort all of these. Then we'll sort, and then we'll take the least k distances. So least k distance, let's suppose, is 1, 3 and 5. So these are least three distances, and then we'll check the labels correspond to these 3 points, the first point, second and third point. Let's suppose it was positive, positive and negative. So by majority vote, we'll say it is a positive element. The query point that we have is a positive. That's the whole crux of KNN. I'll just pose an example, and then you can tell me what is the problem with this, and then we'll try to solve that problem. Okay, so if we had something like this, let's suppose we had a cluster like this. Okay, then we had a point which was like this. Okay, so let's make this yellow. This is our query point. Please focus over here, so that, because I want your answers. How do you think about KNN? Because it's not about telling you the algorithm itself, because these are the problems that you should face, and after that you should be able to answer it yourself, so that we can formalize it. Let's suppose this is the cluster we have, and let's suppose this is the cluster. Okay, and this is our query point. Then if you see, let's suppose we have a point over here, we have a point over here, and we have a cluster, something like this. I made an extreme example so that it makes sense to you. Okay, if we try 2NN, let's suppose, if we try 3NN even, so what is the label this class will get? By what is the label this point will get? Okay, if you see even 3NN, for example, let's suppose, so this will be the neighbor. So this red point over here, so this red point again is a neighbor. So maybe this is again neighbor, and third point is also a neighbor. So even if you see over here, so we had this point. If I zoom in this picture, like this sort of picture, so what will happen in there is, so we have a query point like this, and then we have some points. Let's suppose these 2 points, 1 and 2. Okay, like this. I am zooming it up, and then we had these red cluster points. Let's suppose the red cluster points is a little far, but let's suppose there are a lot more points which are closer to this. Let's take an example. We are seeing not even just 3NN, we are seeing 2, and how many points are there? 5. Let's suppose we are seeing 7NN. Okay, or if you see it, 7NN is here. So if you now compute the distance, so the first 7 neighbors will be this, and then this will be the neighbor, and here these will be the neighbors. Okay, by majority vote algorithm, if you see, this negative class wins. So obviously we can just classify this as negative point. But if you see, like it makes sense to classify it as a positive point. Why? Because it's way closer. Maybe there are more points which are closer to this, and there are less. There is, for example, distance here is very less. So if you compute this d1, d2, d3, and let's suppose this is di distance, and this is our query point xq. For the blue 2 points, we have this blue cross, blue cross. Let's suppose the distance is 0.2 and 0.3. Let's suppose from these red points, if you see, let's suppose we'll take, let's say 5NN, or maybe 5NN. Okay, so if you see the distance of our query point towards this red point, let's suppose this is 0.9, then this is 1.2, and this is 1.4. Okay, by the majority vote, if you see, these red points win. So because if we check the 5 nearest neighbors, and you are obviously seeing that 3 points there which are neighbors are basically these, but it looks that obviously it should have been classified as blue. Why? Because blues are very closer. So if it is only 2 points, but still they have very less distance, 0.2 and 0.3. If you see these 0.9, 1.2 and 1.4, they are the neighbors, but they are farthest from there. Okay, so this is the problem KNN has. So we just found a problem with standard KNN. How many of you are able to understand the problem first? So are you able to understand the problem that is there?
Yes, sir.
The problem is that if there is a point which is closer to one cluster, but the neighbors in that they are closer. For let's suppose there are only 2 neighbors. But what happens is, if we have a cluster which has more data points in it, and then the other neighbors, so there are more neighbors than that, and the distance between this is basically way higher, and distance between these blue clusters is way lower. But still, by our majority vote algorithm, what happens is it will be classified as negative point. That is, it will be classified as red point. So can you propose a solution by which we can overcome this problem if the problem is clear? Again, retaking the problem here looks that we have some points, blue points, they are less in number. But obviously, it seems the distance is very less. That means if distance is less, it means, because we have seen that if distance
Sir,
is
we can
less,
assign weight on the basis of distance.
okay. So distance, I just want greater distance is less. That means similarity is more. Huh? That's what I wanted to. I want to convey. Distance is less and similarity is more. So what is the solution that Rian proposed? He said assign weights. Okay, assign weights. Assign weights to what? To these points. Is it the solution? So everybody understood Rian's solution?
Yes, sir.
So what he actually is proposing is that he's saying that assign more weight to these points, assign less weight to these points. Okay. So how can we, let's call it a weight function now. Let's have how to assign weights. Let's take the Rian's algorithm forward, and we'll say we'll assign weights. We'll assign weights, and now the point is how to assign weights. So can you come up with a mathematical function, or can you come up with factors? So based on the distance, you'll come up with factors. So how to do that? Can you give the answer, Amir, Jahangir, Rian, Umar? How to come up with this a function by which we can assign weights? Now you are saying that when you have these neighbors, for example, whatever the neighbor is, will have some distance, and then multiply. Let's suppose w1 some weight,
Sir, the weight should be inversely proportional to the distance, something like that.
right? So what Rian proposes that we'll say whatever, because distance, as the distance goes down, the similarity goes up. Okay. So we can write that weight wi, we can directly write it, is equal to 1 divided by di. Okay, that's the problem what you guys solved. This is called as weighted KNN. Okay, so that's the reason, if you understood the problem, you should come up with the solutions yourself. So in the standard KNN, all neighbors have equal importance. Okay, standard KNN says that every neighbor is equally important. So we take decision based on that. So weighted KNN, it assigns weight. Okay, it assigns weights to the neighbors. So what happens because of this? So it gives importance to the neighbors. So if the neighbor is really closer, that means there is higher weight is assigned. Okay, now we actually came up with a function also. So we came what we named as weight function, let's call it. So we assign weights, and we came up with a weight function. So as Rian said, that weight function wi, let's suppose, is equal to 1 by di. Okay, so this is our weighted KNN. Is it clear? So can you implement weighted KNN on your own? So how many of you will be able to implement this? Because nothing you have to do, instead of directly assigning a weight and then doing the majority vote. Now what you will do is, let's suppose in here, what we'll do is we'll just multiply these numbers. Now we have these numbers as 0.2 and 0.3. Okay, then we had 0.9, 1.2, 1.4, 0.9, 1.2, and 1.4, and 1.4, and these are our red points, and these are our blue points. So now we'll assign each of these as weight, and we'll multiply by that weight factor, let's suppose. Okay, so this is our, so first, if we add normally these weight, if we add the values normally, so total value we'll get is, for example, this will be 0.5, but we need higher value than 0 because here the values will be more. So what we'll do is we'll do wi multiplied by some di for the summation of all of this. Okay, and then we'll again do summation of wi multiplied by di for all of these points. Okay, now you know that if we say 1 divided by 0.2, so how much is this? 1 divided by 0.2, so this is equal to 5. So we have
5,
5 plus 1 divided by 0.3, just check it, and this is 3.33.
3.3, yes.
So this is nearly 8. Let's suppose 8.3, something like this. Okay, then we have 1 divided by 0.9. Okay, so how much is this? This is 1.11 in this, plus then we have 1 divided by 1.2, so it will be less than 0, so it will be 0.83, plus 1 divided by 1.4, so how much is this? So this is 0.71. If you add these 0.714 and then you will add it with 0.83, then you will add it with 1.11, so how much value did you got? Let me again check it. 0.83 plus, and then I'll say plus 0.71. The exact value is 2.65. Okay, so now these points have gotten all over value of 2.65, and these 2 points got a value of 8.3. So who wins? So these points win, so we'll label it. Now we are not doing majority, we're only changing this. So what we are doing is we are doing weighted sum. So we are taking weighted sum of each class, and then when we take this weighted sum, and after that we'll just compare these sums. If this is a binary classification problem, if you see, you just compute the weighted sum, that's 8.3, and if you compute the weighted sum of this class, negative class, and this is our positive class, so positive class have a weight sum of 8.3, which is way greater than this 2.65. So what we'll say the label of this query point that we had, this query point is, this is a positive class point. The rest of the KNN will remain the same. So what is the KNN again? You will check the distances of all the points and take the topmost, let's suppose 5 neighbors. Here 5 neighbors you will take, and you have the distances with you. So after that you will just multiply it with the factor of weight. So weight function we consider as this, and you can have different weight functions as well. So you can compute your own weight functions. So this is just one example of the weight function. You can maybe do something other, so that the only thing that you have to respect is when the weight should be higher if the distance is lower. Okay, the weight is assigned based on the similarity, how much similar is this point, and you can compute, you can have different functions which will respect this constraint, and you can come up with the functions. And one is this inversely proportional function. Maybe you can add, subtract, make the function complex. It is up to you. So how do you want to decide the weight? It will depend on the weight function that you will compute. Is it clear?
Yes, sir.
Okay. Now you saw that we use this KNN for classification purposes. Classification. So what is the meaning again? What is classification? So in classification we have a data set, let's suppose D, in which we had points xi comma yi. This is supervised learning because we have label also. So let's suppose we have this I is equal to 1 to n points. For each xi belongs to some rd. This means that it's a r-dimensional point. It's a vector of r which lies in some vector space rd, comma this yi belongs to 0 or 1. Okay, so this is a classification. By, if you write it mathematically, this is the meaning of classification. Okay, so we have some data xi, something like this. For example, in our case we had some, if we take about this email, so we had an email in which we had different words in the email. So each of xi was an email, then each of the label was spam or not spam. Okay, that was our yi. This is the setting of classification. So far we have used this KNN for the classification. Okay, now what I want to do is I want to do regression with it. Let me just revise what regression means. So again we'll have the data set. Again the similar thing, we'll have xi, a data point, corresponding label will be yi, such that this xi again belongs to some real d-dimensional space. If it is real valued vector, then this yi will belong to r. So it will take some continuous value. What's the example of regression? Let's suppose you are predicting house prices, you are predicting temperature, you are predicting weather. So this weather value, the label in there can be a continuous value. So the value can be 1.3, 1.8, 6.9, something like this. It won't have classes. Okay, So is the problem of regression clear? So this is our regression. So I'm again and again revising you these terms because so that these things get ingrained into your brain, so that if somebody says regression, this equation should pop up in the head. So because we have a point xi, we have a label yi, xi belongs to rd, that means it's an r-dimensional vector, and yi belongs to r, that means it takes a continuous value from this real numbers. Now I want to adapt my KNN so that it should work for regression. So I can say KNN for regression. Again, I want you guys to answer me. So if you have understood KNN, what KNN does, so now you should be able to give me an answer for this. So in the again in the KNN we were doing majority vote, and then we'll find the label. So what can we do here? So if again making these clusters like this, we have these clusters, and then if we have a query point, suppose this is our query point, if we apply 3NN, so what we'll do is we'll compute the distances from the 3 neighbors. So now we'll get these neighbors and their corresponding distances. Now these corresponding distances, these neighbors have labels, but they are not a discrete number. They are not just 0 or 1. They are now a regression value. They are a value which belongs to R. Let's suppose we have these values x1, y1. This is our first neighbor. x2, y2 is our second neighbor. x3, y3 is our third neighbor. Let's suppose, because we are just using KNN. KNN for this 3NN. So say this is this value basically, so yi again I read belongs to R. Now we have these things belong to R. So initially when we started this KNN, we said that it's we solved a binary classification problem. That time we said this yi belongs to 0 or 1. So it can, the label can be either positive, negative, 0, 1, minus 1, 1, whatever. There will be only two labels. So then we do a majority vote. So in here what we'll do is we'll just take y1, y2 and a simple thing is we'll take y1, y2 and y3, and then we'll add these things up, and then we'll take average of these things. We'll take a mean of these three. Again, because it will give a regression value, because you are taking a mean of this. Now instead of majority vote, you are taking mean. Okay, but you know that mean is prone to outliers, so that it is disturbed by the outliers. You can otherwise take median. Okay, let's suppose we have three neighbors, 1, 3 and 5. So if you take mean, so this is 5, 3, 8, 9, the mean is 3. So you will give it a 3 regression value. Again, but if there was an outlier, let's suppose this 5 was something as 20. Okay, then it seems a little bit disturbed value. It seemed like out of the norm. So now the value you will get is 6. Okay, but if you want your algorithm to be sort of not disturbed by the outliers, you'll take the median. The median still is 3. Okay, that's what I'm saying. So instead of mean, you can take median, but there are both possibilities there. So the first possibility is if you want to convert this KNN algorithm from classification to regression, so what you are doing is you are not doing the majority vote now. So you are taking mean, median, and there are other functions as well. You can take different functions, different mean and median. That's what I want. So the only thing you'll have to change in the first step, if you see what we changed, we assigned the weights. So when we are solving a problem, first problem was because we want to assign weights based on the distances. We computed a weight function. In the second part, if you see the problem that I told you, the problem was I want to use this KNN for computing the regression. Now I want to use it for regression problems. That was our problem. And then how did we tackle it? Instead of doing a majority, we just changed one step. Okay, that's why I want you to understand these algorithms, because many of the times you can come up with your own algorithm, because if you keep on changing different things, so there were some fixed steps like step 1, step 2, step 3, step 4, step 5. In the first case we changed something over here. Okay, we assigned some weights. So in the next problem we change something on this step, because now you have not memorized the algorithm. So you actually try to understand the algorithm from the heart, and what are the steps it's involved, and why is it solving the problem. When you understood it, then when there is a problem, you understood the problem first, and then you were able to see what change should I make in the algorithm. Okay, that is the template. That's the way you should learn. It's not like memorization of the algorithms. The way you should learn the algorithms is, okay, what's the crux of algorithm? What's the intuition behind the algorithm? What is the algorithm basically doing? It's not just doing classification, just doing regression. If somebody poses me a problem, this KNN, there's a failure case of KNN here. Can I readjust my algorithm somehow so that I can implement this algorithm in some different version? And there are a lot of versions of KNN. I'll just name few of them because there are problems. Why am I naming them only? Because you should find these problems and then try to understand these problems well and come up with your own solutions. Okay, there is something called as adaptive KNN. Adaptive KNN. These are named like this, and these are standard names. And then we have something called as, and there are again problems, so I'll tell you where these problems are needed, and maybe after we read about data structure algorithms, then we'll come up again to sort of build new algorithms on KNN. So as I said, that complexity wise, the problem was order ND time complexity and order ND space. This is huge. Okay, so if you want to make this algorithm fast, these algorithms are called fast KNN. Okay, and because we want to decrease the complexity somehow. Okay, in fast KNN we use some other data structures like KD trees. Okay, and then there are algorithms which are called as LSH. This is called as local sensitive hashing. So local sensitive hashing. The problem that we had is this KNN is really slow. If you see the time complexity is here, it's order and it takes a humongous amount of time. Then we wanted to come up with different things so that we can make this algorithm faster. I won't teach you this KD trees right now because you must know what is a binary search tree and things like that. What is a tree in itself? I won't even teach you this right now, LSH, but I promise you that I'll teach you once we are done with reading about these trees and reading about the hashing. But the question is, what I want to understand you at this step is, where can we change the algorithm so that we can make it faster? That's the question I'm asking you. So I'm asking you, where is KNN taking more time? Taking more time. That's the thing we should first be able to analyze. So this is the part where KNN takes most time. I somehow need to find smarter ways so that I can change this part. Again, I'll write the KNN. I'll write the KNN maybe. So what we did in KNN is, so for xi in D train, so we took this xi in D train, and because we had this query point xq, so what we did is, for each xi in D train, we computed the distance of this xi with xq. Okay, and then we saved it in some list, let's suppose. Okay, and this loop was running order n times. Okay, then in the second time what we did is, after we had that list, after we had list D, let's suppose, list of distances we had, then we had to sort it. We had to sort this, sort, even if not, like there are things where you cannot even, you can just keep track, and then you just took minimum number of this. You said, I'll take minimum distances, minimum k distances, but this was our culprit. If you see, order n time here. Okay, and even computing this distance, it took order d time. Each of this operation took order d time. That's why we said order nd. This time it's taking order nd. So are you able to find why is this slow? This is the slowest step that we had. So how many of you understood why is KNN slow? Okay, so most of you understood it, why it is slow. Now we somehow have to find elegant ways by the help of which we can compute the distances faster. Or even if we cannot find the distance first, we must find the neighbors faster. Okay, so this boils down to a searching problem if you see it. So you need to find this. For example, if you see in the direct algorithm, you have this, let's suppose order n, because you are taking each of this point and then computing the distance. But I somehow want to make it faster. So it means that I have to make searching faster. Here, whole of this algorithm was trying to find these k nearest neighbor. It was trying to compute the k nearest neighbors. Okay, it basically is a searching problem. If you see, we are searching for our neighbors and then computing distances. Now we need to use different data structures and different techniques. Okay, and that's why these trees and this hashing comes in. The trees and hashing comes because this boils down to a searching problem. If you know that this hashing has order 1, and when you search for an element, if you have used hash tables, it has order 1 complexity. It searches it in an instant. It does not take order n. In these trees, you can take order log n. How many of you know this? The complexity of searching in a binary search tree, which is balanced, it is order log n, and in hashing it's order 1. Rian, do you know this from data structures course? We'll get into these, but right now think it as like this. So if you want to search something, so if you have this balanced binary search trees, so in that we have order log n complexity. So what is the meaning of order log n? What is the meaning of order n? This means as the input grows, in the similar fashion, we'll see that searching time grows also. Let's suppose for one element, if it takes 1 second, for 100 elements it will take 100 seconds, something like this. So this will be a linear growth. Okay, what is the log n? Log n means, for example, here if you see this log of 100 to the base 10, it means 2. It will take 2 seconds only. You see what's the difference between this log scale? There is a humongous difference between, if, for example, you have 100 elements. So if you perform a linear search, let's suppose each element takes 1 second. So it will take 100 seconds. Okay, if it is in order n algorithm. So now if you have this 100 and this is a logarithmic algorithm. So let's suppose this is order of log n. So how much time will it take? It will take 2 seconds. It will take 98 seconds less. That's why, like, you see the humongous number of seconds that it saved. It saved 98 seconds just for 100 elements. If you consider now 10,000 elements, 10,000, it means 10,000 seconds. So how much is 10,000 seconds? So if you just divide it by 60, so 10,000 divided by 60, so this is 166 minutes, around that. So now if you take this is for order n algorithm. If you have order log n, so what will happen is, so this will take just 4 seconds. For this 10,000, this will take 4 seconds. 4 seconds means even not a minute even. That's the difference between a linear and logarithmic algorithm. So have you seen the difference? Do you feel the difference now? How much important is it to save even a second of time? Okay. Initially, if you feel that, like for example, for one log will pretty much similar for less input. Once you grow the input, and you see here, it grows, the time also grows linearly. So this is time, this is our input, and this is just rough estimate. I just want you to feel these things, and this is our complexity. Okay, so complexity when it's linear, that's order n. So if we have an input which is of 1,000 elements, so we're assuming that one input takes 1 second to process. So here it will take 10,000 seconds. So 10,000 seconds is 166 minutes. That's nearly 3 hours. Okay, and if you see order log n algorithm, if there's an algorithm which performs better than this linear, and it does the work in log n time. So for this 10,000 elements, so there will be only 4 seconds will it take. So from 3 hours to 4 seconds, this is a huge saving of time. And that's how you should know what algorithm internally use. So I told you that this is the time taking part in KNN. So KNN has this part where it computes distances, and then it arranges it, it does a lot of stuff. So the crux of whole KNN is to find the nearest neighbors faster. So it basically boils down to searching. So I said in searching we have trees. Okay, in searching we can search something in order log and time. Okay, so if you have this balanced binary search trees, you can search in order log and time. That's what trees give us, this data structure. And in hashing, you make what's called a hash table. So the hash table gives us the searching in order one time. Okay, this is a huge topic in itself. This is a huge topic in itself. But now we have tools by the help of which we can do searching faster. And by using these tools, we can make our KNN faster. So how many of you understood this discussion? Again, my point here is not to teach you the algorithms. My point is rather to teach you how to think. Okay, how to find these connections, how to see this finding is actually a searching problem, how to see that pattern. Okay, we're trying to do this, actually is a searching problem. Can I use trees for this? Okay, and can I use hashing for this? So when you are accustomed of thinking like this, is what I mean by algorithmic thinking. So I was talking about algorithmic thinking, I think, in some session. So in there I said you should think algorithmically. So this is the algorithmic thinking. So when you see something, you are thinking in algorithmic. Oh, I am finding this is in brute force. Are there ways so by which I can reduce the time? This is what I want you to learn. So I promise you these things that I'll teach you. Both are this tree-based approach of KNN and hashing-based approach. For hashing, it's called as LSH, local sensitivity hashing, which I wrote, I think, somewhere here. Okay, adapt to KNN, maybe you'll have to look it up. But these two things, after you are done with understanding what a tree is, what a binary search tree is, what are these things, and how to compute the complexity, and then we'll go about this. And even hashing itself is a huge topic. When we are done with the hashing, that time we'll again come back and see how to implement this. But I will strongly urge you guys, whenever you are done with the data structures like trees and this hashing, you try to do it yourself. Okay, that way you learn a lot. Am I clear? So I said chains we made in KNN, chains we made in KNN. Okay, if you just see what are the steps that are involved in KNN. The first step was to compute distances of query point, or we said test point, whatever it was, XQ, from all dtrain points, from all points in dtrain. Compute distance of query point from all points in dtrain. This is our first step. And what is the second step? Find k nearest neighbors that you know how to find. The third point was to do the majority vote. These were our major 3 steps. So in the first step, when I told you that if you have to find k nearest neighbors, you will use Euclidean distance, and then we had a problem with that because you wanted to assign weight. This is the step we changed. So how to find this? So this is the step that we changed in weighted KNN, where we assigned the weights. We found the different ways to compute this, and then in the regression, we changed this portion in the regression. So when we had to change this algorithm from classification to array, we changed this step, majority vote. Now we did not do majority vote. We computed the mean. And in order to reduce the complexity, to make this algorithm faster, we changed this step. This was for fast KNN, because we wanted to compute this faster. Okay, and then you can mix and match it. You can change every step and see what is the effect of that. I hope that all of these points are clear. Now I'll move to the next topic.